And that's goal-seeking in semiotic systems, value to space colonization by Briar Frisk. He is an independent researcher with Arcology Solutions as well. So there's a fair bit of arcology in this conference, actually. He works with Arcology Solutions, which Stuart does as well, and singularity.org. And focus on semiotic AI for autonomous systems in harsh and resource-constrained environments. The last bit sounds very interesting, and I'm sure we're going to see what semiotic AI for autonomous systems are. Briar, floor is yours.
Thank you. All right.
You're probably sharing the wrong screen.
Okay. Oh, yep. Sorry. Does that look like the a slide?
There you go. Yeah.
Okay.
Good.
Got the slides.
Sorry about that. Move that off screen. All right, yeah. So my main project is working on something called Gaia-OS. Originally started with Stuart and Arcology Solutions, and it's to make a adaptive environmental controller for space was my original goal, so that fits here. And this is sorry, it's pretty early here, so yeah. So this is just output from the system. This was a proof of concept I have working so far. So this is just kind of old stuff here. And it has photographic memory, controls generalization. It's not a black box. It learns from unlabeled data and for causal relationships, predicts deviations. And the point of this, I'll get all into this in future slides, but for the moon, we need systems that are edge devices because there's no internet up there when you get in the craters and whatnot. And even if they're, like the latency between Earth and whatnot, you don't want to be dependent on that because any dependency is death if something goes down. Like if the stuff isn't in situ makeable, then if a part breaks and you have to order it from Earth or something else, that's a problem if it's a critical life support system and you don't have a backup. So on the moon, yeah, there's no internet in the crater. They must self-explain themselves if they're a safety critical system, like if your O2 scrubbers or your Nicholas mentioned pressure is a big concern. If something goes wrong with that, you want to know why so that you can prevent it in the future. And so it has to be able to show itself internally. Yep. And so the current solutions for autonomous systems don't really work for the moon or space in general because you can't safety certify them for one thing, or the big thing, because they're stochastic and they're non-deterministic due to the backpropagation they use. Because they take the network and you just create a big array of nodes and you kind of randomly initialize it and burn the patterns in. So different training can get different results. So it's not the same output for the same input. It's not, you can't really view the interior very well since it's not symbolically grounded. You have to bolt on systems to try to infer what the system is thinking, which is not optimal. And safety certification, from what I've seen, requires things to be like no dynamic allocation, it has to be fully traceable, whole bunch of stuff that you just can't do with those systems. So the current solution is to wrap them in a ton of software and constrain them to either non-safety stuff or have them extremely bounded, and it's extremely costly, and it's a kludge. It's not a very good solution. So these are a little out of order, I'm sorry. And so the solution I think is like the semiotic systems I'm working with, they're fully grounded, they're fully explainable, and they're deterministic. So with that, you can then, like, say you have one controlling the air scrubber or a pressure sensor, and it creates a malfunction. You can go back into it, get the log data, and then see exactly why and where it made that decision that led to that failure, and that allows for interrogating the interior of it. It can give confidence scores because it uses individual symbolic traces. So if it gets to a situation where it doesn't know what it's doing, it'll have very low numbers of memory to draw on, and its confidence will be low, and it can report that. If the and Yeah, so that's pretty much that. And so the goal is to get one that is certified. Yeah, sorry. So the goal is to get a certified machine learning core and then extend that to a certified environmental controller or a goal seeker system. And so for security element out of context is the current target. From what I can see, that's the best thing to aim for. And so right now I'm going through, I have a proof of concept built, which is first slide images were from. And now the trick is to take that and rewrite it from scratch to be in line with all the specs and everything needed. And so the goal is to get to SO4 level, which from C is one of the higher ones. So that would open up for automotive, space, airborne, all that stuff. But more importantly, for the future of lunar society or moon society and lunar colonization, it will allow us to have safety certified systems that are actually trustworthy and capable of inference and function approximation. And yeah. And so the over system that is the controller that I'm working on, and it operates in a inference loop. It takes the current state of the system, and then it creates a projection based on that, based on what it's seen before. So if it's seen, turning on pump A causes pressure to decrease, pump B causes pressure to increase, it can learn that and it'll be like, oh, the pump is on, and I know that causes a decrease in pressure, and based on previous mappings of the memory and the motions through time, it'll create a prediction. And then from that prediction, it gets the deviation from the goal. And like in this might be your optimal pressure, this red line. And so it says, okay, in the future, we're predicting that we're going underneath the red line and we need to correct. And so it creates a trajectory mapping and deviation mapping, and then pulls from that by taking the deltas, inverting them, and then what's the term? Bucketing, grant converting it to a signal that is stored in memory, because you don't want to store continuous signals because that's expensive, and memory space is going to be extremely constrained on edge devices. So the one thing you can do to mitigate that is to reduce the data granularity down. So instead of like having a temperature range of 0 through 100, you'd have temperature ranges like 0 to 25, 25, 50, 50, 75, 75, and you just call that like 1, 2, 3, 4. And that allows you to capture the necessary changes and stuff for feature extraction to give the system the ability to control. And with some things you want finer control, some things you want less fine, but generally the lowest granularity you can go with gives you the best memory optimization. But so then it takes the delta to pursue, it takes the current trajectory, the delta desired, and the goal state. And what that does is it'd be like, okay, here's my starting conditions, here's the direction we need to go, and here's the desired state to hit at the end of that. And then it will search the memory, and because it's um, subsymbolic and composable, it can search and it'll find like a memory has a couple pieces here, it has some of the delta here, and it's kind of close to the goal state here, and it can do partial matches, and it generates a inference by collecting all those output symbol traces, and then you can sort them and be like, okay, I want ones that exactly match the initial conditions, and it'll sort all the others out. Or you can be like, I want ones that match within 5 points of the initial conditions, and you can control how fine-tuned the output is. And that's controlled generalization in these semiotic systems. And then from there, all these traces are superimposed and it extracts the control signals from them. And so it can go, okay, the pump is currently on, the pressure is dropping, predicted pressure is going to be low. So we want to bring that up in the future, and to avoid the deep dive. And then it searches like, okay, here's this, we need to not have it dive, and we want it at this. It compiles all the previous memories it's seen, and it goes, oh, okay, I turned that pump off, and then the predicted trajectory would smooth out. And it does prefactor analysis through that. So it looks at the data, gets its current trajectory, finds out where it's going, compares it to where it wants to go, and then thinks about how to get it back on track. And that's the Gaia OS, the main loop of that. And so the goal of certification, looking through all that, it looks like the most of the design parameters and the thing that requires the complete rewrite from scratch, because the C++ code works, it's on GitHub, but it would just take way too much to complete, to refactor that for safety. So to just restart from scratch with what we know. And then the goal will be to drop the core as public domain with the verified compiler tool chains, the failures and all that, and trace matrix, test harness requirements, and with C++ containing the triple redundancy, CRC, no dynamic allocations, safety, all that good stuff, with the goal of having a primitive at the end that is a inference module, that a goal seeker built on the inference modules, that is available to integrators to drop into a system, whether it be a pressure control, environmental control system, or a lunar rover systems balancer, and to be able to go, okay, here's my safety case, here's the system, and then this will give you a head start, and then you just need to wrap it in your existing safety case, so it's no longer a security element out of context. It'd be a security element in context. And this should drop the price floor for doing that thing for autonomous systems, and it should allow for, that's pretty much the goal. Drop the price and open it up, because we can't have closed proprietary systems all over the place running all the life support systems. That'd be a nightmare. And the idea is to open the core, and then the service model would be for training, certification, and all that, and consultation. And the goal of those would be to support the organization that stewards the work. Because, anyway. And so that was kind of scattered brained, but that's the presentation. And currently I'm working with Eco Islands LLC, Colin Linux, for his SOABs, and we're actually, I got parts on the way right now. We're putting on a Raspberry Pi. It's integrated with the I2C and all that stuff. And then Arcology Solutions, which I met Colin through, and Singularity Metal, working with them to make it into a general purpose environmental controller. So that like there's be the bioreactors, which I'm working with Colin on. Then we need the greenhouse controllers and, just all the environmental systems need handling. And Singularity, I'm working with Metal of Singularity to on the back end for the her systems to use these semiotic neural networks for explainable AI. And looking for people who are actually in the industry because I'm self-taught and I have a lot of blind spots. My specialty is on these systems, not on industry or the outside. So yeah, that's pretty much it. And then there's a link to the current GaiaOS repo, which is the existing system written in C++, 11, no dependencies. It compiles, I know, on Linux, or at least the Linux systems I've tried. I can't speak for Macintosh, and it compiles on Windows, last I checked. And then that's my email, and yeah, that's it.
Sorry, I need to turn on my audio before I say something. Thank you, Briar. And are there any questions? I think Marufa has one.
No, I was just clapping.
Oh,
I mean,
sorry.
good presentation.
Oh, thank you.
Thank you.
Thank you.
I have a question, Briar. So in a lunar colony, there are going to be many of these in different systems, right? What's your vision on how to control multiples of them? Is there a higher level semiotic neural net that you connect them all into? Or is that a different kind of a problem?
Nope, that would be so these GaiaOS would emit the I call them treetops, but it's the upper level traces, the upper level. So for every input set, you have a higher level representation node, and those nodes can pass between the networks, and you treat them as inputs. So all you do is stack the networks, and if you want another semiotic system on top, you could put another Gaio on and treat the lower ones as primitives, to where it's like, okay, I know these signals from this GaiaOS are the ones that we want, and then it can coordinate them. Or if you want a more traditional or bare bones system, you could do that too, to where it just pulls the confidence scores, current trajectories, the deltas, and all that from it, because there will be side channel information for every part of this, which is part of the safety requirement. So for every state and all the internals, there has to be a way to check them without modifying their logic. So just from that, we can pipe that into higher level systems. For example, we're working with Derek. I can't remember his last name at the moment. Sorry, but he's part of ArcologyX now, and he's working with the Matter system, which is a more industry standard one for consumer devices. And the way we're doing that is we'll have a smaller module, and then you can have like a consumer grade app. And so if it's a family or something, you can have the family to where they could check their fridge, and then they could check Gaia, and the Matter would be able to pull those from Gaia without influencing the core itself, unless you want to put those feedback loops in and be able to change settings from the app. But yeah, so you could either have a higher level AI system such as this, or you could have a more dumb controller, for lack of a better term, on top, depending on your needs and desires.
So you could also just have a network of them so that they're the ones that need to share signals can share signals between them. It doesn't, then you wouldn't need to have a hierarchical control. It could also be a network control, right?
Yeah, so if you have, you could take the side channel output from one, like say the confidence score, and you could pipe that in as an input to another, because these systems accept any scalar or quanta as the input. Like the systems I'm writing, they use uint32 or uint64 underscore t in the C++, and as long as it can be reduced to a single value, it can be read in as input. So yeah, you could say like, here's the confidence score from the bioreactor and pipe that to another one. And then that one just tries to like maintain the, okay, well, confidence score is a bad example, but you can pipe different outputs from the internals, or you can share goals. So you could have the temperature, and then you could have multiple ones stationed around if you got smaller ones, because these are the safety puts a lot of overhead on it, so they won't be huge. You know, you're probably not going to have LLMs, at least not for a while or anything like that. But and then you could, yeah, you can have them share sensors, temperatures, stuff like that. And if one controls a couple controllers, a couple pumps and heaters over here, another one might control a couple coolers and whatnot over there, and they can coordinate that way, but it wouldn't be as efficient as or as good as a whole system. But yeah, they can coordinate through the edges by routing inputs.
I have a question also. You were describing it as one signal in, one signal out, and obviously that's more. You can handle much more. But how many variables can this handle? Both monitored variables and how many can you control with the same?
So that will come down to because the original Gaia, the one that is the test, it is written to be however many you give it. And this test right here was with random assortment. I think there was 15 controllers and 25 sensors, and it was able to maintain that. And so you can extend it to as many as you want and give it control over, but it has to be a system that is actually controllable and actually stabilizable. And you have to fit it to the memory constraints you're working with. So like this one right here, you know, it might require a larger controller, whereas if you just got a small greenhouse, you can get away with a smaller one. It mostly depends on the power you have in the system, because it pulls from the memory traces and generalizes across them. So yeah, it's multivariable. I've tested up to pretty decent size. That's monovariable. I gotta go to more. I'm working with Common Linux right now, and that's one of the goals there, is to test out, like, in a real system, how much can this handle? What are the, you know, what are the capabilities of it in a dirty system? That's stress testing it and figuring that out. So that's still kind of up for review, but it seems to be pretty good at controlling bigger systems. Oh yeah, I do have a document I can post later too to the workshop or Slack that is the experiment I did to see how it did with different levels and how it fell into cyclical control patterns and stuff like that. But yeah, I don't know. Hopefully that answers that a little bit.
I think that one of the system or two systems I can think of that would be interesting for test cases. One is the Melissa. It's the European Closed Ecological System project. And I think Biosphere 2 is still sufficiently functional. One could probably get past records. And there must have been millions of different ways that people had to make minor adjustments manually that your system would allow you to have something to work on. That, yeah, these are some of the critical points that need to be addressed.
Alrighty, yeah, that would be useful to get the Biosphere 2 data, yeah, because then you could train it and see how it does with a walk forward analysis pattern, and yeah, that would be. Thank you. I'll look into that.
Well, one of the two of the variables that they had to deal with is changes in solar intensity from day to day, and outside temperature that they had to adjust the inside temperature. So there were challenges that I think still must be going on. I believe that the system is at least partially functional yet. And the engineer who designed it is alive, and there's lots and lots of documentation.
Alrighty. Yeah, that's
Frida, I can. Oh, sorry, Briar, go ahead, bud.
Oh, I was just gonna make a comment on how that's one of the things is that the dynamic changes over days and day and night cycles. There's a lot of dirt in the data that needs to be handled.
Having been to Biosphere 2 here for the Analog Astronaut Conference just a couple months ago there, I was presenting pretty much for all of our ecology solutions, but I can speak to what Kai Stats is using in the SAM unit, which was the original Biosphere 2 section. And sorry, getting over a bit of a cold. They're primarily looking at CO2 now within the SAM unit. And it's my determination that I think Briar's ahead, probably by a couple field goals. As far as the complexity, what Kai Stat's team is looking at CO2, O2, temperature, pressure, because it is the SAM unit, it is a pressurized vessel, and that's about it, which is good. His system is also on GitHub. It's open source. It's Raspberry Pi. It's also done in Linux. So that's one of the things that Briar and Dr. Stats, Kai Stats, who's running the thing, they may be trading kit, so that we're training his units up on the the SOAPs that I'll be talking about tomorrow. But yeah, Frida, that's a real good point. And we are actively looking at trying to get Briar's stuff in over there because I think he's ahead of the game. But I'm biased because he's one of my people. Thanks, Briar, dude. It's a great presentation.
Thank you.
So, I have one more question. What if the system is inherently chaotic? I hadn't really thought about this before, but have you thought about that, Briar? Like some systems are just chaotic and there's no real controlling them. So it seems like there'd need to be some kind of a detector and you'd have to maybe redesign the system so that it wasn't chaotic. Or maybe the semiotic neural net would be able to control a chaotic system. I'm not really sure.
Well, it depends, I guess, how chaotic. If it's just complete chaos, then probably not, because it has to learn the patterns and infer them from the past. So if there's no stable patterns to pull from, it wouldn't be able to. But things like a door opening in a greenhouse and sending a blast of cold air, once it sees that and it learns how to build the traces to get it back on track, like it does some exploration because it's low confidence. I gotta go back to that point in a second. But if it has the traces built in to handle edge cases such as that, it'll know how to handle them, but it has to have them in its memory first, or it has to be able to explore and find them. And that's a big thing there. And with safety systems, that's going to be harder to do because live training with a safety certified system, unless they have a new way to certify them in the future, that is an issue because you have to have the training data verified before the system is deployed. Although if you have a greenhouse and you go through and you have a stable floor plan and you train it on these edge cases, then you could get that certified as long as you can prove that it's bounded and explainable and within safety parameters. You also want to have fallback to a safe case, so if it does get chaotic and the system loses its ability to control it, it's like, I have no idea, and it outputs like super low confidence score and says that the delta is not returning, I need help. You can drop back to a certified safe state, or alert a human to get them in the loop and be like, hey, system's crashing, we need help here. And so like right here, each one of these lines is a different memory, and each of these positions along here is a different sensor or different actuator. And this is the same mapping right here, but heat mapped. And so once it has the traces in memory, like right here, it's kind of fallen, this black spot might indicate like in the past the door opened and right here's a blast of cold air, and then it knows like, oh, okay, these are the control patterns to get it back on track. And as long as it has the memories in that it can pull from, it can bring it back, assuming that that will do it, like turn on the heater by the door brings it back on track. It can then account for that.
Thank you. And we need to cut there to continue with the next presentation.